All right, good morning, everybody. Hope everybody had a good yesterday. So today we're going to finish up a few things in chapter 4. We'll get into chapter 5, 5:1 to 5:4, and then we'll talk a little bit about the exam, and we'll talk about the additional question and answer sessions that we'll do before the exam. I'll give you some details about that kind of stuff, and then we'll wrap it up for the day. So last time we finished off talking about alkyne acidity for the terminal alkyne. And we've learned that this hydrogen is unusually acidic for a hydrocarbon because of which effect? The hybridization effect, that's right. So that is that single bond that you have right here is an sp hybridized orbital that holds those electrons. Sp hybridized orbitals can get the electrons closer to the nucleus. Negative charges next to a nucleus that's positively charged is a stabilizing effect. And so that's why these are more acidic than your typical hydrocarbon. And we learned that we can react that with a strong base, something that's known as amide. Don't worry too much about that, okay? So I'm not showing the counter ions that are there. We're just showing the net ionic equation. And we can get a reaction to occur that gives us a carbon-carbon triple bond with a negative charge on that terminal carbon plus ammonia, which happens to be a gas, okay? And so we know that the equilibrium lies far to the right because the equilibrium constant is 10 to the 13th. That's a huge number, right? You could pay me 10 to the 13th pennies and I will be a very, very rich person, okay? Just kind of give you an idea, all right? And so I'm not drawing the reverse arrow. You know, this is essentially not an equilibrium reaction, right? The equilibrium lies so far this part, you just consider it done. Okay, we don't worry about the few molecules that may not have gotten deprotonated. And so what you recognize is that you start over here. This acid is the stronger acid because it has a pKa of around 25. This is the weaker acid, which has a pKa of around 38. And the equilibrium always favors going from stronger acid, stronger base, to weaker acid, weaker base, right? And so that's why you end up with this reaction going this way. Now, why is this going to be important? In the next set of chapters that we cover, we're going to start talking about reactions. What can these things do for us, right? The main thing that you want to do in organic chemistry is you want to put carbons together. You want to make new things. That's the whole trick. More Nobel Prizes have been awarded for figuring out how to take two carbon atoms and put them together than any other single concept known to humankind. Why? Because it's important. Your biology puts carbon atoms together to take the sugars and the proteins and the things that you eat to make new things that you need. All of the stuff that we take for granted in our modern society relies on the fact that we can put carbon atoms together. And so these things can actually react with other things. So for example, I could react that with something like a ketone, for example. Okay, and what I will get out of that is a new carbon-carbon bond. Let me write in some stuff so you can follow it just a little bit clearer. Okay. We just made a carbon-carbon bond. But to do that, I had to start off with a terminal alkyne. I had to remove its hydrogen, and then I had to react it with something else. And we're going to learn about these things as we go on. But what I want you to recognize is that I think you can obviously see that this is an acid-base reaction. This too is an acid-base reaction. What is the acid? No, we don't have ammonia anymore. It's gone. I'm just talking about the reaction of this plus this to get this. You're right, it is the resulting conjugate acid of the top reaction. So looking at that bottom reaction, what's the Lewis acid? Let me step back just a second. What is a Lewis acid? Seps electron pairs. Which of those molecules is accepting an electron pair? The ketone. Right? This has an electron pair. So it's the electron pair donor. So it's a Lewis base. This carbon is going to accept that pair of electrons to make the new carbon-carbon bond, and you're going to break a weak pi bond and put those electrons on oxygen. This is called a reaction mechanism. How we're pushing those electrons to make the bonds that we need to make and break the bonds that we need to break. Okay? This is our Lewis base. This is our Lewis acid. And so it's very, very important, again, that we be able to identify Lewis acid, Lewis bases. It'll help us figure out the type of chemistry that we got going on. Okay? Now, if we take a terminal alkyne, like we have here, and we react it with a weaker base, the reaction doesn't go. Not very well, anyway. Can you tell me why? Right, we're going from this, right? We're going to react it with hydroxide, which you all learned in general chemistry is a strong base. For organic chemistry, it is not. And I figured out by looking at the acids. The pKa of this is around 25. The pKa of water, we'll just call it around 16. I'm going from a weaker acid to a stronger acid. That is not a favorable thing to do. So the equilibrium is going to lie to the left. And it lies so far to the left that this reaction essentially doesn't go. Okay? So being able to compare acids tells us an awful lot about what kind of a reaction we've got going on. Okay? And so table 4.1 shows you some of the pKa values of these different substances. And so you need to know roughly where these things fall. You know, the pKa of an alkane, is around 50, 51, an alkene around 44 or 45, and an alkyne around 25 or 26. Those need to be memorized. You're going to need those as you move on. Okay? Those pKa rough ranges are pretty good. And water has a pK of around 16. Okay? And so you can clearly see the effect of the hybridization effect, right? sp3, sp2, sp. Definite changes in the pKa's that we're seeing. Okay? Because as we increase that S character, if you will, that is to say there's more S character in the orbital, the more acidic that compound will become. Okay? So that finishes up 4. Let's get our model kits out for a second. Let's spend a little time going over some stuff from chapter 4. We learned last time about alkenes, carbon-carbon double bonds, right? We have a sigma bond and a what bond? Pi bond. Which one's stronger, sigma or pi? Sigma. Which one's weaker? Pi, right? And why is that? the orbitals, how they overlap, right? So the p orbitals that are left to make that pi bond are just barely touching each other, and they're not as stable, right? And so there's not as much overlap. But a sigma bond has really good overlap, and that makes for a really strong bond. Okay? So let's think about a molecule that has an alkene. How would you name that? Cyclohexene. Do I need a number? I don't need a number. Why don't I need a number? No matter where I draw that double bond, it's always going to be the same number, right? So we can just ignore it. So I can make that with 4 sp3 hybridized carbons and 2 sp2 hybridized carbons. Okay? And to do that, I am going to connect these together like this. And I now have cyclohexene, and it's going to sit almost like a chair, like we talked about before, a little bit. It's going to have a little bit of a lopsided seat. I'm not going to be able to be too terribly comfortable on it. But nonetheless, I've got my cyclohexene. What's the geometry of that double bond? I think you're not exactly. It's not bent. What's the configuration? Let's call it that. What's the configuration of the double bond? Is it E or Z, or is it cis or trans? What is it? How do we figure that out? How do we figure out if that's cis or trans or E or Z? Okay, yeah. We know that if the high priority groups are on the same side, we're going to call that Z, right? As long as the same side. We've learned that little corny thing, right? Or we can also call it cis in this particular case, right? They're on the same side. So it's a cis alkene or a Z alkene. And I know that by looking at each one of the carbons. If I look at this carbon, I know it's attached to a hydrogen and a carbon. This takes higher priority. If I look at this carbon, it's attached to a hydrogen and another carbon. This one takes high priority. And both high priority groups are on the same side of this plane. Right? Now, I dare you to take your model kit and make the trans alkene. And trouble getting them together? Try to make it trans. That would be taking one of these groups and putting it over on the other side, right? So that they're trans to one another. Try to make that work. Hard? Make it trans? That's no longer cyclohexene, is it?
Yeah, no.
Just take cyclohexene and try to make it trans. Take one of these off and try to put it on the other side. What happens? You think that's going to exist? No. In fact, you can't form trans cyclohexene. It's always going to be in the cis conformation. Do you think we can ever get to a point where we can easily have trans? Let's try that. Let's add another carbon. So instead of cyclohexene, we would now have cyclohexane. Yes, 7 of them is heptane, right? So heptene. So I can easily see putting it together in a cis conformation. Can I get it to where it's, let's see, still pretty bent, but is it more or less bent than before? A little less. So we might be able to make that. What about if we add one more carbon? What would that be called? Cyclooctene. Yeah. So let's see what happens when we do 8 carbons now. And what do you think? Better again, right? Now let's put, what did we just have? 8. Now we're going to go to 9. So it's cyclonamine, right? So can we make that? What do y'all think? That doesn't look too bad, right? Maybe a little bit bent. But around 8 or 9 carbons, you can start to get a trans cycloalkene. 6, 5, 4, 3, absolutely not. It's going to be hard, okay? And so the length of your chain that's connected to your alkene will determine whether or not you can have cis or trans isomerism in cycloalkenes. Okay? 1, 2, 3, 4, that's what I want. Up here, we'll go back to cyclohexene. You all said that the name of this was cyclohexene. What would the name of that be? I'm seeing a lot of things saying methyl cyclohexene, okay? But what about the number? You may have said it and I didn't hear it. 1, right? We're going to number through the double bond. And this is going to become 1 methyl cyclohexene. What if I do this? What's that name? Again, it is 1 methyl cyclohexene. Why is that? Yeah, we're always going to start at the double bond to give the double bond the lowest number. And we're going to start on the side that gives us the lowest number to all of our substituents. What would the name for that be? 2-methyl cyclohexene. Let's see if that's right. 2-methyl cyclohexene. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. I don't think we can get a 2-methyl cyclohexene out of that, right? So which one's this going to be? It's going to be 3-methyl cyclohexene. Right? That's going to be the lowest possible number I can get everything, including my double bond. What about if I did this? Let's do that. And let's do that. What do we think now? Repeat it, please.
2,4-dimethyl-cyclohexene.
Where are you starting your numbering?
At the bottom of the diagonal?
Here?
No.
Here?
Yeah.
So 1, 2,
No,
1, 2.
Yeah.
But we have to number through the double bond, remember?
1, 2. Oh.
Right? We don't just start at the double bond, we have to number through the double bond. So that's an important thing. We want the double bond to have the lowest possible number, that's true, right? But you have to then go through to the next carbon, right? So if we start here at 1, which you suggested, let's do that. So that would be 1, 2, 3, 4, 5, 6, which would be what name? What do we give that? 4,6 dimethyl cyclohexene. Okay? Or if we number it the other way, 1, 2, 3, 4, 5, 6, we would have what? 3, 5 dimethyl cyclohexene. Which one's correct? That gives the lowest possible numbering for everything, doesn't it? Okay? Don't forget you've got to number through that double bond. You don't just start at the double bond, but you do start at the double bond, but you number through it. You can go around and set your numbering system up that way. Okay? All right. So today we're going to start talking about reactions of alkenes. Alkenes, the carbon-carbon double bond, is a functional group, and the functional group is the pi bond, and the pi bond is weak. Weak bonds are not stable by definition. Sigma bonds are strong. So it's going to turn out, what we're going to figure out is that these reactions of alkenes, typically they undergo what are called addition reactions, and so we're going to start talking about that. We're also going to start introducing the idea of a reaction mechanism. And we've talked a little bit about that. Okay? We've talked a little bit about that. But we're going to talk a little bit more about it. And we're going to talk about the fact that carbon is in a special place in the periodic table. I've told you all that more than once. Carbon is in the Goldilocks area. Not too hot, not too cold. Just right. Carbon likes to have 8 electrons, but it can have fewer than 8 electrons to form intermediates that are very reactive. And that allows these reactions to occur. Okay? We're really fortunate that carbon can do this because it's how our bodies are able to assemble molecules from things that we eat. It is why we are not silicon-based, because silicon doesn't do this, even though there's a lot more silicon on the Earth than there is carbon. Okay? Just walk out on the beach and you see all the silicon that forms, right? But we are not silicon-based life forms, we are carbon-based life forms, right? So we're going to talk about all of these things today. In general, what you need to know is that an alkene likes to do an addition reaction. So if you have some carbon-carbon double bond, it will react with some reagent. We're going to learn different types of reagents. And what we're going to find is that we can add X and Y across the carbon-carbon double bond. We can add X and Y across the carbon-carbon double bond. We just got to learn what X and Y are or can be. Okay? And I know that this reaction is going to lie to the right. Why do I know that that reaction is going to lie to the right? Why do I know that? Just by looking at the reaction without doing anything with numbers like you all did in general chemistry. Yeah, I have to admit, I really don't know why we have you all start in general chemistry. We have you start in general chemistry, we give you a calculator, we start calculating all this stuff, and you just start calculating stuff because somebody told you how to use an equation, right? I'm looking at this, I have no calculator, I have no numbers, but I know the reaction has to lie to the right because my chemical intuition and my chemical common sense tells me it must be so. Why is that?
Sigma and pi bonds.
Sigma and pi bonds. I am sacrificing a weak pi bond. Anytime I break a bond, it takes energy. You will learn in your biology classes and even in biochem that breaking a bond gives energy. That is absolute nonsense. Do not buy into that. You do not break ATP and get energy by breaking the bond. Okay? All bond breaking events require energy. Let me repeat that again because it's important. All bond breaking events require the input of energy. They are all endothermic. Do you get energy from ATP? Yes, but not from breaking the bond. Okay? There is no such thing as a high energy bond. You can't have something that's unstable that exists like ATP exists. Okay? So where do we get the energy from ATP? The bonds that it forms after it breaks. That's where you get all the energy. Because all bond forming events release energy. I'm forming a bond between X and carbon and Y and carbon. And they're strong bonds. They're sigma bonds. So I know that this reaction is going to lie to the right. Yes, I've got to break this bond as well. But look, I'm breaking a weak pi bond. I'm breaking a relatively strong sigma bond. And I'm gaining two strong sigma bonds. I know this reaction is going to go to the right. Okay? It's going to be favorable. Is it going to go to completion? I don't know that yet. That's where I need a calculator. Okay? But I know it's going to lie to the right. And that's important. Okay? And we know that the pi bonds are weak because you all told me that the orbitals, the p orbitals, don't overlap very well. But where are the electrons in that pi bond? Are they between the carbons? Or are they above and below the carbons? They're above and below, right? So if I'm a reagent coming in to react, is that easy to get to or hard to get to? Really? That's easy, right? I can get to that pretty easy. Now if I try to get to the electrons in between the two carbon atoms, that's a little harder, right? I got all this stuff hanging around. But coming in from the top or the bottom is not too tough. Okay? And so it turns out that these pi bonds are kind of like dangling their electrons out, just waiting to be reacted. Okay? You can think of it kind of like that. Okay? In general, everything that we're going to talk about for the rest of the term comes down to this one slide. Can you identify strong bonds and can you identify weak bonds? If you can figure that out and put a little acid and base chemistry with it, you've mastered chemistry. Really. You really have. Okay? The only difference between you and me at that point is that I got a lot of years of experience and I've read a lot more and that's it. But you can catch up, right? No problem. All right. You should also recognize that it could be possible to add X and Y on the same side as I've done here, or on opposite sides. That's possible. It's possible to add things on the same side or on opposite sides. Okay? When the two atoms are added on the same side, we call this syn addition. When they're added on opposite sides, we call this anti-addition. So I can add X and Y in a syn fashion or in a anti-fashion. Okay? And it turns out that the mechanism of how these things work will determine whether or not it happens in a syn fashion or an anti-fashion. Okay? So if I say the anti-addition of something across a double bond, what comes into your mind is that that double bond is going to have those two groups added on opposite sides. If I say the syn addition of something, you need to know that it's coming in on the same side, making the bonds on the same side. Okay? So we can have syn addition and we can have anti-addition. For the purposes of exam 1, we're going to limit exam 1 to this set of reactions. You need to know these reactions. I highly recommend you all build road maps to memorize these things. What is a road map? A road map is a sheet of paper. So imagine this being your sheet of paper. And at the top, you label the reaction type. Something like that. Addition to alkenes, however you want to name it. In the middle of the paper, you put the functional group that you're doing the chemistry on. In this case, we're doing the chemistry on an alkene. So your book has just picked cyclohexene as an example. That is the functional group that I'm starting with, is in the middle. And now I'm asking myself, what in the world can I do to torture that functional group? Or convert it into something else? I can convert it into a lot of things. I can, for example, add HCl across the carbon-carbon double bond. And I can get that functional group. Now, I could also add chlorine, bromine, or iodine. You see how they have it listed there, right? So how could I even make that a little more easy? I could just say HX, where X is equal to chlorine, bromine, or iodine. Make it a little more generic. What halogen is excluded? Fluorine. Fluorine does not do this chemistry. HF does not do this chemistry. But HCl, HBr, and HI will do this chemistry. If you take an alkene and you put it in the presence of dry HCl or HBr or HI, it will add those two atoms across the carbon-carbon double bond. My starting functional group is what functional group? Yeah, the alkene, the cyclohexene, yeah, so it's the alkene. What's my new functional group? This is called an alkyl halide. It's got a halogen. So guess what? I can convert alkenes to alkyl halides very, very easily. I can also convert alkenes to dihalides. Notice a halogen atom is on both there's one halogen atom on each of the carbons that start off being the alkene. So I can take an alkene and I can make a 1,2-dihalide. Where do I get that name? Di meaning two, halide meaning halogen. What halogens work here? Bromine and chlorine. Iodine doesn't do this. Okay? Fluorine doesn't do this. If you try to do this with fluorine, F2, it goes boom. If you do it with iodide, it just sits there and stares at you. Okay? So what are you trying to memorize here? You're trying to memorize patterns of what the chemistry can do. Okay? What else can we do? Well, I need a little bit of sulfuric acid. So if I take sulfuric acid and water, I can add water, H2O, across the carbon-carbon double bond. This is called hydration. Where is that important? What class of molecules do you all know something about in nutrition that has something hydrate in it?
Carbohydrates.
Carbohydrates. What are carbohydrates? Carbohydrates are sugars. They're sweet. They're energy. You know, we eat them, we get energy, right? They're nothing more when you break it down. They are nothing more than pure carbon and pure water that came together at some point in time. That's what a carbohydrate is. Okay? I've taken a hydrocarbon, and I've added water across the carbon-carbon double bond. It turns out I don't need a lot of sulfuric acid for this, it's catalytic. But if I take this hydrocarbon, this alkene, and I put it in water, it'll stare at me for about 1,000,000 years. The reaction is really slow, but I add 1 drop of sulfuric acid, it speeds it up, and I get a reaction that occurs fairly quickly. What does a catalyst do? What'd you learn in Gen Chem? Speeds up the reaction, but is it consumed? No. It doesn't end up in the product. It speeds the reaction up, but it is not in itself consumed. So you don't need a lot of it. Okay? I can also do a 2-step reaction. Notice this, it says 1 BH3 and then 2 H2O2 and hydroxide, which is just basic conditions. What have I done here? Have I done anything different than the previous reaction that I showed you? No. It's still adding water across a carbon-carbon double bond. So why in the world do I need another reaction? Well, we'll learn about that this semester. There are things that this 2-step reaction gives us in terms of the product that are different. You just can't tell from the chemistry we're doing right now. Okay? We'll learn about that. This is called hydroboration oxidation. It's a 2-step sequence. What this means is that we first add this, and then we add that, and ultimately we get that product. So when you see a single arrow with 1, and then whatever, and then 2 with whatever, that means do the first thing first, and then whatever you get from that first thing, you take on to the second thing. Okay? So you're kind of learning this. And we can also where X is chlorine and bromine. Oh, X. We can form what are known as halohydrons. We can add OH and X across the carbon-carbon double bond. No problem. Okay? Why would you want to order it like this? What's convenient about building a roadmap?
Which direction it is.
Okay,
You don't have to keep on drawing your cyclohexane.
That's true. That's true.
You can see where your derivatives are coming from like its origin.
Okay,
Easier translation of ideas.
okay. I like what I'm hearing across the board. If you built individual flashcards for each one of those reactions, you would treat them perhaps as if they are fundamentally different. They are not fundamentally different. They are fundamentally the same. You just get different products because you have different things that you're putting into the reaction. But fundamentally, we are breaking the weak pi bond and we are generating 2 strong sigma bonds. Fundamentally, we are doing the same thing. I am not saying that the reaction mechanism for all of those reactions is identical. I'm saying it's similar. When you start to build these roadmaps, if somebody said, well, I've got an alkene to start with, but I want to get to this, it gives you a starting point. You can start to think about it. When I look at this, I go, look, I can take an alkene and I can make alkyl halides. I can take an alkene, I can make halohydrons. I can take an alkene, I can make dihalides. And I can take an alkene and I can make alcohols. I am doing what's called functional group transformation. I am taking what I was given, the alkene, and I am transforming it into what I want. So if I went up to the lab today and I found out that we needed cyclohexanol, which is the alcohol on the top, but all I have in my lab is cyclohexene, I don't just sit back and go, well, I guess I can't do my work today. No, I'm going to take my cyclohexene, I'm going to put it in water, I'm going to add some sulfuric acid, I'm going to boil it for a while. And I'm going to make my cyclohexanol. And then I'm gonna use it to go on and do whatever I want, because I can take these functional groups and I can transform them into anything that I need to transform them into, within reason. Right? I can't convert it into gold. Okay, that's transmutation. Can't do that, but I can do a lot of things nonetheless. Okay? You need to know these 1, 2, 3, 4, 5 reactions for exam 1. Okay, what would be fair game? Fair game would be me to give you the starting material and the product and ask you what you need in the middle. What would be fair game would be for me to give you the starting alkene, the reagents, and ask you what the product are. At this point, that's what's fair game. I'm not going to give you the product and say how you're going to make it. Not yet. That'll come in later chapters. Okay? But right now, if I gave you an alkene and I gave you a product, so let's say I gave you cyclohexene and I gave you cyclohexanol, the alcohol, you need to know what to put in the middle. Right? Sulfuric acid and water. Okay? So, those are fair game for the upcoming exam. All right, so let's look at some examples, right? So here we have an alkene reacting with HBr. We know we're going to add the hydrogen and the bromine across the carbon-carbon double bond, and we're going to end up with this product. So I go from an alkene to what we call an alkyl bromide. Okay? I take cyclohexene, I add HCl, I end up with, how would you name that? What would the name of that be? Not quite. What's the parent? What's the parent hydrocarbon, or the parent chain?
It'd be like 1 hydro, 2 chloro.
Do I need to number the hydrogen? What do we number? Substituents, right? Okay, so do we consider hydrogen a substituent? No. So we're going to circle the ring, right? That's our parent chain, which is what? 6 is what? It's cyclohexane in the product. It's cyclohexane. What's the substituent? It is chlorine, and we call chlorine chloro. So technically you could call it 1-chlorocyclohexane. Do I need the number? I do not. No matter where I put that chlorine, it's always going to be number 1, so we just call it chlorocyclohexane. How about this one up here at the top? How would we name that? What's the parent? No, that's the substituent, the parent. What's the parent chain? 2 carbons is what? Ethane. Yeah. So it's an ethane parent. What's the substituent? Bromine is the atom, but what's the substituent? Bromo, right? So this is, put it together, bromoethane. Yep. Do I need a number? I do not. I do not need a number, right? This is bromoethane. Very good. Okay? Now, how in the world does that work? Here's an example. We're going to add HBr across an alkene. And we're going to start off pretty simple. We're going to start off with this alkene. Name that for me, please. What's the parent?
1, 2, 1, 2. Yeah.
You got to find the parent, right? How many carbons are in the longest chain? 2?
4.
4. Right? We got 4 carbons in the longest chain. So it's a butene. Can I just call it butene? No, I've got to put some more in there, don't I? But it is a butene parent. I'll give you that. We're getting there.
2, 3, 5.
Remember, this is the longest chain, right? So do I have any substituents? I don't, right? Okay. I don't have any substituents because everything's taken into the name of the chain, right? So it's a butene. Do I need any numbers?
No.
Ooh, I hear a yes and a no. So if I told you butene, do you know where to put the double bond? Could I put it at carbon number 1? I could. I could have CH2 double bond, CH, CH2, CH3, and that would be butene. But where's the double bond start here? Carbon number 2. So this is a 2-butene. Do I need anything else? Sure. No. Now I got to look at the geometry around this, right? The conformations and configurations around this, right? This carbon and this carbon. Notice the groups are different on each carbon.
Oh, it's Z.
It can be Z2-butene, or we can also call it what other name? Cis. I would take either one.
Interchangeable, Z and cis.
They're interchangeable here, yes. I will say for small molecules like this that are this simple, most people go with the cis nomenclature. Okay? Okay. Let me just redraw it. Now we're going to react this with HBr, so I'm going to say plus HBr. Which one of these groups do you think is the acid and which one do you think is the base?
HBr.
Is which one?
The acid.
The acid.
Yep. So this is my Lewis acid. Also turns out to be a Bronsted acid, but I don't care about Bronsted. We shouldn't even teach their theory anymore. So that's our Lewis acid. What does that mean? Well, it does donate a proton, but that's the Bronsted-Lowry theory. What's it going to accept? It's going to accept an electron pair because we're using the Lewis acidity definition, right? So it's going to have to get a pair of electrons from somewhere. Where's it going to get them?
Carbon.
Which carbon?
Either one.
Either one. Okay, I'll buy that. Really where it's going to get them is from the pi bond. The pi bond, what is a bond? A bond is a pair of electrons. Okay, so that's going to be where it's going to get its electrons, and so that means that this alkene is a what? If this is a Lewis acid, this must be a Lewis base, Lb, right? When I'm drawing a reaction mechanism, I always start my arrow pushing at the Lewis base. And I start at the pi bond. And where am I going to draw that to? I'm going to draw it to the Lewis acid, but am I going to draw it to the H or to the Br?
BR.
Why? Why am I going to draw it to the H and not the Br?
Because the H will accept the electrons.
It will, but why? What is on BR that I'm not explicitly drawing? Lone pairs. Do you think a pair of electrons is going to want to start getting around a bunch of other electrons? No, right? And if I think about HBr, that's a polar bond, right? Bromine's pulling electrons to itself, so that puts what on hydrogen? Is this a polar covalent bond or a covalent bond? It's covalent, but it's polar, right? Because bromine's pulling electrons to itself. So this actually has a partial positive charge, this has a partial negative charge, it's got a dipole that goes in that direction. Okay? So my electrons from the pi bond are going to react with the hydrogen. Notice I'm using a double-headed arrow. A double-headed arrow tells me that I'm moving 2 electrons, or 1 pair. Okay? Notice where I'm starting. I'm starting at the electrons in the pi bond, and I'm moving those to the hydrogen. How many bonds can hydrogen have, though? 1. Isn't this kind of suggesting that I'm forming a bond to hydrogen to give it 2 bonds? Kind of am, right? So something else has to happen. What else has to happen? A bond has to break. Which bond am I breaking?
The bond between hydrogen and bromine.
That's right. And so those electrons are going to go on to bromine. So I'm taking a pair of electrons here, and I am going to make a bond between one of these carbons and hydrogen. Does it matter which carbon at this point? It does not, and it does not because they're absolutely identical. You get the same thing regardless of which, right? You can see that this side of the molecule is perfectly identical to this side, so it doesn't matter. And so what I get this. Where this hydrogen, let me just put a star on it, is this hydrogen. Just so you can see where it went. Okay? So that pi bond has formed a sigma bond with hydrogen and given me this carbon. That carbon has a positive charge on it, though, doesn't it? Why does it have a positive charge on it?
It's the hydrogen.
You're right. No need to cover your mouth. You're right. The electrons in the pi bond went to hydrogen, right? How many bonds are now around carbon? 3. If I circle that and do the math, how many valence electrons does carbon come in with? 4. How many does it own now? Right? If I circle it, it comes in with 4 electrons, and it now owns 1, 2, 3. It has a formal charge of +1. Does it have an octet? No, it does not. So do you think this is going to be reactive or unreactive? Do you think I can put this in a bottle and it be stable and be happy and I can go back and look at it tomorrow? No. Carbon sits in the second period of the periodic table. It would like to have an octet of electrons. Again, carbon sits in that position on the periodic table where it's got a sweet spot, right? And
Here's
so,
some information.
yeah. Okay. Where can it get another pair of electrons? From the bromide. I'm just being accurate, okay? You're right. This has lone pairs of electrons around it, right? So this was the Lewis base. This was the Lewis acid. If this is the Lewis base, then that becomes the conjugate what?
Acid.
That's the conjugate acid, and bromide is the conjugate base. Acid-base reaction, acid-base reaction. There's my product. Okay, what you see there. Okay, that is the product. This is the start of a reaction mechanism. I'm showing how the electrons are flowing, how they are moving to make the new bonds. The arrows, by definition, are not showing the movement of atoms. They are showing the movement of electrons. And because the electrons move, so move the atoms. A lot of people will make mistakes and say, oh, this hydrogen goes there, so let's just draw an arrow to that. That's not what we're talking about. We're talking about the electrons. Lewis base to Lewis acid. Lewis base to Lewis acid. You have to be able to identify Lewis acid, Lewis bases all the time. That's what's going on in these reactions. Okay? Now, what we have drawn here is represented on this energy diagram that you see here. Okay? What is A and B in this reaction?
Reacting.
Those are the reactants. So this is A and B. And they're at sun energy. As this bond starts to reach out and make a bond with the hydrogen, right? We're having to break that pi bond, and we're going to have to start breaking that sigma bond. We're going to have to put energy in, right? And so the energy goes up to what's called a transition state. Transition states don't exist for very long. You go through a transition state, okay? This is kind of representing that transition state, okay? Then we end up with an intermediate. That's this carbocation. Carbocations are called intermediates. What does it mean to be an intermediate?
You're in between.
You're in between. What am I in between there? If I look at that intermediate on that diagram, what am I between?
Transition states.
I'm between two transition states. Intermediates are always between two transition states. But they're not something that I can put in a bottle. They're not stable. I can detect them. I can take my magic microscope, I can go into the lab, and I can see a carbocation for a very short period of time. I cannot see the transition state. Transition state is the highest point on the mountain. Imagine you climbing up to a tall building that comes to a spire that's just a very tip of a point, and you walked all the way up there and you stood on that very tiny point. How long do you think you're going to stay there? Not at all. You're going to go through it. You're going to step up and you're going to fall down, right? That's what the transition state is. This is the energy of activation. We've got to put energy in for this to work. We go through a carbocation intermediate. Then I have a new transition state where the bromide is reacting with the carbocation. Notice the energy of activation, right? The activation energy for step 1, is it higher or lower than the step for step 2? Why? I'm breaking a lot of bonds, right? What am I doing in the second one? I'm forming bonds, so the energy has to be lower, right? So once I form the intermediate, the next transition state is so low in energy that it happens almost instantaneously. And I end up with my products C and D, which are, in this case, just this, right? This is a reaction energy diagram. What do you need to know for the exam for the reaction energy diagram? I will be giving you an energy diagram and pointing to something and saying, what is this? You need to know, is it starting materials, is it products? What are the energies of activation? What's the intermediates? Where are the transition states? Okay? I don't always tell you what's going to be on an exam, but this is going to be on the exam. Okay? You're going to have to be able to identify the pieces of a transition state. All right. Last topic for today. Then we'll talk about the exam. You need to know this rule. It is Markovnikov's rule. And we will learn more about Markovnikov's rule later, but today we're just going to do the basic foundation. The addition of HBr in the previous example happened to a symmetrical alkene. That means the left side and the right side were identical. That doesn't happen all the time. I could have an alkene that looks like this. This carbon is clearly not the same as this carbon. This one only has hydrogens attached to it. This one has a methyl group attached to it. So when I add HCl, across the carbon-carbon, I have two possibilities. I can add the hydrogen to carbon 1 and the chlorine to carbon 2, or I can do exactly the opposite. And actually, only one of those products forms. Okay? And it's not this one. It's two chloropropane is the only product that forms in this particular reaction. This is Markovnikov's rule. So if you look at this, notice I have two hydrogens on this carbon and one hydrogen on this carbon. Which carbon of these got the hydrogen of HCl? Carbon number 1 or carbon number 2? Carbon number 1. Markovnikov's rule states that in the addition of HCl, HBr, or HI to an alkene, the carbon atom of the alkene with the most hydrogens gets the hydrogen. So all you have to do is look at the alkene and ask yourself, which of these two carbons has the most hydrogens? It's this one. So this one gets the hydrogen, and you end up with 2 chloropropane. Right? There were already 2 other hydrogens located there. So again, I'll asterisk that one to be that hydrogen. You need to know the definition of Markovnikov's rule. Okay? We were slated to get into some carbocation stability discussions today, but I'm going to exclude that from the exam. I'm going to save the next 10, 15 minutes so that we can talk about the exam, because I know not all of you can attend probably the tutorial sessions or the question answer sessions. So I'm going to offer a session on Saturday, and I'm going to offer a session on Sunday. They will be upstairs on the 4th floor, not in this classroom. I repeat, not in this classroom. They will be upstairs on the 4th floor. I will send something by Candace. Question is, what time of the day? So for Saturday, what time of the day?
Is there, what's our time, span that we have available?
I'm going to be here all day Saturday and Sunday because I've got a proposal due. So I'm going to take an hour each day to come over and do what I need to do. So
Like after 4?
which day?
Either.
Saturday morning, what time? Okay. So how about we do this? How about we do something in the morning on Saturday and something in the afternoon on Sunday? That work?
Super Bowl's on Sunday.
That has priority.
Super Bowl starts at what, 6? 6:30? So we won't do it at 5. How about Sunday at 2?
Yes, that's great. Sunday too.
Saturday? 10? 10? So 10 a.m. Saturday, 2 p.m. Sunday. I will record. Pardon?
I was gonna ask if you could Zoom record.
I will record. I will not Zoom. So it will be recorded and posted by Monday. I can't promise exactly when. But basically, I set up a camera. It faces the blackboard. I walk in with 0 agenda. I am not going to teach anything new in terms of content in the book. Okay, so you all walk in, you start asking questions, I start answering, and we go from there. It'll be probably 4:11, but I'll put that in the other thing, or in the email out. All right, so we've got that settled. Now, you all have an example exam from back from 2006. you will not see that exam. It just gives you an idea of how I ask questions. So let's talk about the exam itself. It will be 25 questions in length. You will have one bonus. Answering the bonus is to your benefit. It will be the same point value as the other questions. If you get to the end of the exam, just bubble something in if you don't have time to think about it. It's to your benefit, okay? There are no penalties for wrong answers, okay? These will be multiple choice, but you do have to work things out. If you think you can answer these questions simply by reading them and finding something that sounds right, I've included all kinds of different ways that I know you all will think about these things that are wrong. Okay? So you got to work it out. There will be a space. So you'll have a question, whatever, whatever, whatever. You will have your choices, and then there will be a thing that says work here. And you can write, you can do whatever you want to on it to help you figure out the problem. Okay? What I will tell you is that students who actually work their problems out on the exam typically score 10 to 15 points higher on the exam than students who do not. Okay? So, work through your problems. Okay? And you'll move on. Now, we use what's called a zip grade form. You do not have to buy these. They will be included for you. Works just kind of like a Scantron. You will have a space up here for you to put your ID number. You will have to put your student ID in that space. Because when I take a picture of the exam, it automatically grades it and it sends it to my grade book for your grade. If you do not have your number in there correctly, it will not get automatically populated. And then I have to go and figure out who you are, and then I get upset. And that's not good, right? So, make sure you know what your ID number is. Many of your student IDs will have something like these starting zeros are not your ID number. It's the first non-zero number. My ID number is 536,947. So I would put in 536,947, and then I would bubble in the bubbles underneath it. I would circle those in. The zip grade form can use pencil or pen, as long as it's dark. Do not do this in pen though. You cannot hardly erase pen. I highly recommend pencil, okay? But you will have a zip grade form, and you will have a place to where you can mark each and every question, okay? When you are done with the exam, you will turn in the entire exam. You cannot take any of it with you. You cannot take a picture of the exam. Okay? You just turn it in and you go on your way, okay? So that's how that works. Because it's in zip grade, I should have the grades to you by the end of the day. And usually what I will do is I will post the grades, and I will also post a message. Okay, so if you see your grade and it's not exactly what you were hoping for, do not panic, do not go press the eject button on the class. Okay? Don't do that. Wait till I send stuff out. Come talk to me if you had concerns. Okay? What are you allowed to have on the exam? You may have your handwritten notes. You may bring in your notebook that has your handwritten notes that you took in class. Those notes cannot include a direct transcription or copying of the book. Do not feel like between now and then you can just copy the whole book. Okay? You cannot have that. You cannot have your book. Okay? But you can have your handwritten notes. You can have your model kit. Have pieces put together. I recommend having a 6-member ring put together with a few other carbons hanging off of it so that you can just manipulate and do whatever you need to do. Okay? You do not want to spend your time during the exam clicking pieces together. You just want to be able to pop them together to figure out what you need to figure out. Okay? So, you can have your model kit. You can have your handwritten notes. And I will provide the zip grade form, so you don't need to worry about that. And I will provide a periodic table.
So what about like charts in the book, like the acid and the strong acid,
You can have, let me put it to you this way, if you need to know an exact pKa value, I will give it to you. But you're not gonna need that. You need to know the rough regions of the pKa. Now, you can put in your notes that kind of information, but don't just replicate the table. Okay? Any other questions? Yeah.
In anticipation for this, are you gonna give a practice exam and its answer key on campus?
You have the old exam that I did way back in the day, and that's all I give. No keys.
Is the PowerPoint same considered as like the book? If I write something from the PowerPoint, would it be considered like book terminology?
If it's your handwritten notes and it's not a direct copy of all my PowerPoint slides, it's fair game. And can you take a piece of information from the PowerPoint slide and put it in your handwritten notes? Of course you can. You can do that with the book. I mean, if you wanted to write a definition of a word in your notes, you can do that. You just can't copy the whole book. All right? So, what's going to be covered? The first day of class, the materials that we covered that weren't in the book, those PowerPoint slides, all that information is fair game. Everything to today is fair game on the exam. And I ask a little bit from everything. Okay? So it's all going to be there. That includes, now y'all know, there's some things that or your reading assignment, and we didn't cover a lot of it in class. It's fair game. Okay? Those are topics that I felt you could grasp on your own and we didn't have to spend a lot of class time on. Okay? So everything in the reading, everything that we've covered is fair game on the exam. Okay? Any questions? All right. See some of you Saturday, see some of you Sunday, and see all of you next Tuesday.